Hello everyone, I am Jiawei Chen, and just as he introduced, I'm going to be presenting our work on synchronous programming with refinement types in robotics, from verification to implementation. So, at the high level here, cyber-physical systems, or CPS, are software that can interact with the physical environment, such as this drone right here. The thing about CPS is that they tend to be held to very high standards of reliability, so it makes them a natural target for formal verification. However, there's an issue here. Languages that are usually designed to be easy to verify CPS typically either don't produce executable code, or they require some extra steps and effort, which increases the trusted base. On the other hand, we have languages for CPS that are primarily designed for implementation, but now we have this issue where they trade off the precision for expressivity. And so these might be pretty difficult to verify. So here we have these two circles here that represent verifiable CPS languages and executable CPS languages. We believe that CPS designers shouldn't need to choose between verification and implementation. So the question we want to ask here is there a language that can support both? So today, I'm going to convince you that synchronous programming with refinement types can produce CPS programs that are both verifiable and executable. And we have an entire robotics platform that we've developed on top of this principle. So at the core of our language and our platform here is this notion of synchronous programming. Now, synchronous programming has some very strict rules on what can manage data or what can access memory. And so this makes it a nice choice for emulating or modeling embedded systems that might have limited computational or memory resources. So this is great for modeling embedded systems, which typically run most CPS. Now, it turns out we're in good company here because synchronous programming has already been proven robustly in industry, such as, for example, the languages like Lustre, Scade, Estavel, and Signal. In fact, if you flew in on an airplane to Splash, chances are really good that the autopilot on that airplane was written in Scade. So, synchronous programming, the main takeaway here is that it views data in your program as streams of values that can change over time, and programs are manipulations or operations that change the behaviors of these streams. So for example, here we have a simulation in a language called MARVeLus, which is the language that we use to base the synchronous core of our platform on. Now, MARVeLus is typically thought of as a hybrid system modeling and simulation language, but we also note that the discrete time semantics very closely resemble Lustre, and that's what we're going to be focusing on for verification. Now, what's really good about MARVeLus is that it is written in OCaml, and it can actually generate executable code that is typically run in simulations. What's good about having things in OCaml is that we can then integrate this easily with C programs, such as those that are found on real-life robots, such as the low-level drivers. And so this is going to be key for us taking verified code written in some language that's similar to MARVeLus in our platform, and integrating it easily with C-based drivers to actually execute things in the real world. Now, another important component that we've enhanced synchronous programming with is refinement types. So here's just a simple variable declaration. If you've written any sort of strongly typed programming language, you're pretty familiar with this notion of having a variable that we specify with some sort of type, and we assign it with some term here. So let x of some type float equal 3.14. You can obviously see that this type checks because 3.14 is a float. Well, let's try to add some additional information to these types here. Let's say we wanted to enhance it a bit. Let's say we wanted to specify that x is not only a float, but it resembles some v here, which is a binding variable, which is a float, so base type of floats, such that it satisfies this refinement predicate here, v greater than or equal to 0. And so what we're doing here is we're saying that this x needs to satisfy this predicate here, so it must resemble some v such that v is greater than or equal to 0. As you can see, 3.14 is non-negative, so obviously this type checks. So the key takeaway here is that we want to be able to say something about the terms of your program within the type. Now, the reason why we want to do this is because type checking is basically automated push button verification that is already embedded in most programming languages that support types. So if we add some additional constraints to these types with refinement types, we basically get verification of additional richer software properties, such as, for example, the safety of your program, or that maybe some terms of your program don't take on dangerous values. What's really important about having refinement types, though, is that it limits the kinds of predicates that you can put inside your type spec such that it is SMT decidable. Now, this gives the user, or the CPS designer here, the confidence of a definite yes or no answer as to whether or not their software can either check, or perhaps there might be a counterexample. Now, we take inspiration in our type system from Liquid Haskell, and you may notice that some of the type refinements here and like the binding variables, they very closely resemble this notion of liquid types. And so we're going to talk a little bit about how we integrate this into the rest of our platform. So one really important distinction that we need to make from just taking Liquid Haskell and implementing it in like MARVeLus, for example, is that stream refinement types express temporal properties. So we just mentioned that all of our programs, all of our data, they're basically manipulations on streams. So if you have some X, it might not be the same value if you look at it sometime in the future. So let's take a look at the stream definition here. So we have a let rec X, and we have some type spec, and we'll get to that later, but we essentially have some 0 followed by X plus 1. And what this refers to is the stream that starts with 0, and at each time step, it increments its value by 1. So this is a recursive definition of a simple stream that goes up 0, 1, 2, 3, 4. Now we add this temporal operator, and if you're familiar with linear temporal logic, you'll notice that we have this box or global operator. And so essentially it takes our simple refinement type here of v greater than or equal to 0, and it expands it out to say v is not only greater than 0 now, but it is greater than 0 always and forever. So here we've taken a property that might say something about a single value, and we've extended it out to express some property on an entire stream of values. And this is going to be crucial for us to establish safety properties in real programs. Now let me introduce you to MARVeLus, and that's what takes all of this and puts it together. And so it stands for the Method for Automated Refinement Type Verification of Lustre. And here's just a flow chart of the entire robotics stack that we've developed. We have like specifications and code that the user provide. This gets fed into a type checking step that is powered by an SMT solver. This gets fed, once it type checks, it either gives us a counterexample that the user can then use to refine either their program or their specifications, or if it passes, it sends this intermediate representation to the base MARVeLus compiler, which generates executable code that then passes to our robot runtime extensions to execute on actual robots and hardware. So the key takeaway about MARVeLus is that we allow verification and execution in a single language by carefully balancing expressivity with verifiability. And we believe that synchronous programming with refinement types gets us that. So to summarize here, our contributions are as follows. So we enhance the specification system by allowing refinement typing rule, by enhancing the original type system with refinement typing rules that are based upon this notion of synchronous programming. We then implemented these typing rules in the MARVeLus type checker, and so this gives us our automated verifier. And then finally, we extend the MARVeLus runtime with the ability to control real robot hardware, like sensors and actuators, such as on this little robot right here. Now, we're going to walk through a simple example of an adaptive cruise controller. So we have autonomous vehicle braking, which is a component of adaptive cruise control, or ACC. Now, what autonomous vehicle braking does is it continually looks ahead of a vehicle, and it senses if an obstacle is becoming close to your vehicle. And if it's too close, then it needs to slam on the brakes to avoid a collision. Now, obviously, this is a really important safety feature that you definitely want to be reliable. So this seems a natural choice for formal verification to handle here. So in our example here, we're going to assume that hardware abstractions and sensors are trusted. So we always get good data out And we also trust that, for example, any commands that we issue to the controller are going to be respected by like the low-level drivers. What we're really interested in here for MARVeLus is verifying the control logic that runs the software at like sort of a high level here. So a nice natural safety property to have with autonomous vehicle braking is specifying that the distance between your vehicle and a wall, for example, never goes to 0. So essentially, you never crash into an obstacle. So we want to say that box distance is always greater than 0. So one of the challenges of being able to both verify and execute CPS is the fact that you need to be able to say that some sort of implementation level software, or you need to be able to switch between implementation and verification. And what I mean by that is that when you execute things on a, let's see here. Okay, so when you execute things on a robot, you have to deal with real hardware accesses. For example, you might have a line of code, such as this right here, that actually says we want to either read a value from a sensor or we want to write a value to a motor. But the problem is you can't really verify this, because if you just read from sensors, it doesn't really tell you about the physical world. You're just saying we want to read whatever's the immediate value from like the sensor. What we want is offline verification. So we don't want to actually check our code while the robot is running, because if you need to run software to verify it and something bad happens, well, it's too late to do anything about it. Your robot has crashed into the wall. It's a bad time. So instead what we do is we require the user provides a model to verify. So right here highlighted in blue, here's, for example, the model of how the distance of the robot, and so the distance reported by the robot sensor changes based on its velocity at the present moment and some other parameters. So this is a physical model that we expect the user to ensure that this model reflects what actually happens in the real world. And so this is really the responsibility of the designer to give us an accurate model on which to verify. So the key method here to reconciling the model with the actual implementation is this sort of switch right here. So this models keyword. So in this code snippet, we have some physical model of the robot's sensor and the values that it is expected to give the controller. And then it's separated here by the models keyword with the actual implementation, so how it gets real world values from sensors. And so this is a switch that can be changed between either the model for verification and simulation or the actual implementation at compile time. So you can either check or you can execute. So of course, we also have built-in functions that we've added to the language to allow for accessing sensors and actuators. And you've noticed here we have like robot get right here and robot store right here. And they're essentially, they just provide us with a rewrite interface that we're able to then extend out to different types of sensors on like the robots. So here's what so let me just remind you again, here's the automated braking system. And we're going to implement this in MARVeLus code for real. So first, let's define a helper function here, just need to brake. And this is just a simple Boolean value that it returns. It's either true if the robot is close enough that it must brake in order to avoid a collision, or it's false if the robot is free to do any sort of other action, such as like not brake and just kind of coast. Next, we're going to define some constants here. So these programs need to be verifiable and executable, so they need to be provided concrete values to allow for deterministic execution. So we've just defined some simple system constants here, such as the starting velocity of the robot, how far it is away from the obstacle initially, and the maximum braking power that it is able to apply. Next, we're going to write down the base type spec. So this is essentially telling us that we have essentially a state vector of distance, velocity, and acceleration, and they're all floats, and we put them together in a tuple here so that we're able to describe properties that involve all three variables together. Now next is the safety condition. So this is just d greater than 0, and you notice here that we've dropped the box because everything in our programming language here, they're all streams, so all these properties, they're always going to be universal anyways. So d greater than 0. But this is not quite enough because this is not an inductive property. So let's say that in some time step n, we put the robot 1 millimeter away from the obstacle, and we set its velocity to like 10,000 meters per second. Now, obviously, given the brake power that we specified here, the robot is not going to stop in time. But even though we've satisfied this d greater than 0, there's no way the robot's going to make any action that will prevent a collision in time step t n plus 1. So instead, we need to define some inductive invariants to strengthen what we have here as our initial specification. Now, namely, the first inductive invariant that we introduce is what we call the forward decision invariant. Essentially, what this says is that whatever happened in the previous time step, we can assume that the controller has made the right decision. So obviously here we have, if it doesn't need to brake, then it doesn't really apply any sort of acceleration. If it did need to brake, then it would have applied the correct acceleration or like the appropriate action at that time. The next invariant that we introduce is the dynamics invariant. And what this essentially is saying is it encapsulates the various laws of physics that govern how the robot's distance changes over time based on its braking power. So essentially this is saying that whatever we did in the previous time step has left us in a state such that if we perform the correct decision in this time step, then we have enough time to safely stop, and so therefore we are able to avoid a collision in this time step. So this is all about induction. It's basically saying that we assume we did something right before, and if we're able to perform the correct action now, then we have ensured safety for the next time step too. So here's the start of the actual executable part of the program. So here we're defining some initial conditions, such as the starting position of the robots, the starting velocity, and the starting acceleration. And so this loads up the initial state of like our state space model here. Next, we define the evolution of the system dynamics. And let me point out here, this is the models keyword we were talking about before. So everything to the left of models here, like for the next velocity or the next distance, we define the kinematic model of these parameters such that if we simulate it, these are the values that it'll take when it tries to verify or simulate. But on the right-hand side of the models, we have the actual implementation here. So this is where it reads from real-life sensors when we execute onboard the robot. And so essentially what we're doing here is we have this models keyword that lets us switch between the model and the actual implementation. Finally, we have the controller here. And just for simplicity, this is a very basic controller. It basically says that if we need to brake, we brake. If we don't need to brake, then we don't need to brake. But obviously, you can define more complex controllers, such as if you want a proportional control or something that varies the braking power, such as like anti-lock brakes. You can define that here. But the reason why we have this control invariant look very similar to the follower control is just the fact that we've defined a very simple controller for this example. Now, this might look like a lot of specification here that we need to do to verify a very simple program, but all of these specifications are vital to proving the correctness inductively of your stream program. So to illustrate that, we're going to take out one of these invariants. Namely, let's try to take out the control invariant here. So let's assume that our program might have not taken the correct action in the previous time step. Well, when we try to verify this, we end up with a counterexample. And so this counterexample here tells us all the variable assignments that cause the robot to enter some sort of unsafe state because it didn't account for the fact that in the previous time step, it might have not made the correct action. So here we've given the user some interface to be able to diagnose any problems that might occur either in their specifications, such as here, or if there's like a genuine bug in their code, here's a way for the user to track down where those problems might occur. So the verification aspect of this, so like once you write your code, the way things verify is that we take these typing rules that we've developed for synchronous programs, and we generate verification conditions, or VCs, from those rules. Now these VCs need to encapsulate these global temporal properties, And for now, we only specify global temporal properties or any sort of LTL formulas with boxes in them, because we note that these are enough for safety in most cases. Because when you define a safety property, you either want something to always happen or never happen. So we believe this is sufficient for most cases. Now, once we have these VCs that are defined based on our typing rules, we pass these along to a satisfiability solver or like an S&T solver such as Z3. And that's what gives us either a pass or a fail and then a counterexample. Now, I mentioned before that because we're working with streams, we have to account for changing values within our streams. And likewise, our typing rules must also have some sort of temporal notion to them. For example, here's the typing rule for a branch statement. So just a simple if then else statement. Now, a lot of this might look a little familiar, but we have to introduce some extra conditions into the branches here to account for the fact that your conditional here is also a stream. So it's not only true now, but it could also be, true, false, or it could just stay true, but it has to account for the fact that the conditional might actually change over time. And so therefore you need to make sure that your branches respect this fact and they also behave correctly based on this changing value. So that's just one example of a rule that we had to modify from standard refinement types in order to account for the temporal aspect of streams. We also note that if you take recursive definition and followed by, which is stream composition, you basically get a proof on induction. So here we have the let rec rule. This is pretty unsurprising, and it's just your typical let rec rule. And then followed by here basically says that if you have one stream composed with another, they must have the same temporal property attached to them. And so this is essentially like saying, if we have a base case here and the recursive call, we have induction if we can prove the property on both of these. And the let rec lets us introduce recursive references. Now, obviously, this is not an entire type system. And if you want to look at some of the other rules that we've had to adapt, feel free to look at the other typing rules in our actual paper. Now, we didn't just create this type system and write down all the typing rules and just called it a day. We actually decided to implement this and test it on real robots here. So we took that code that you just saw a moment ago, we verified it in MARVeLus, and then we actually executed it on a real robot in our lab. In fact, we executed it on this little robot. Cute little guy, right? So this is an MBot Mini. This is originally a robot designed for a robotics class. It's a teaching tool, so it's very modular, pretty inexpensive, and really well documented. Now, some of the nice features about this MBot is that it includes a LiDAR, which we use to measure distance of obstacles around the robot. It also has a BeagleBone Blue as its main processor, and it runs Linux and also the entire MARVeLus stack. And so this is what actually does all the control. And then finally, it's got some wheel encoders that let it measure its own velocity. And so here's a graph of some actual data we took from one of these experiments. So the orange trace here represents the actual values recorded by the robot while it was running the autonomous braking demo. Now the blue traces here, the blue trace here identifies the values that we got out of simulation. So as you can see here, the lines are pretty close to each other. So it's good to see that what we proved and verified in theory actually applies to practice here. So our robot didn't crash in the lab. We don't have a hole in the wall. So of course, MARVeLus exists in a world of other works that try to strive for a similar goal here of verifiable and executable CPS. For example, we have tools like Sci-Fi House and Verify that also promise end-to-end verification and execution of cyber-physical systems. However, they note, for example, that either they work at high levels, such as with coordination of multi-agent systems, or they assume the existence of some verified controller that they can safely switch to. Whereas in our case, we focus more on the lower level kinematic controls, and we actually assert this verification of a proven safe controller. So we're the ones that actually design the safe controller that perhaps a sandbox controller might fall back to. And now verification via types has also been explored before, and specifically in robotics too. So the Ross-Cock tool uses the Cock theorem prover and dependent types to verify certain properties on message passing protocols of sensors and peripherals within robots. And Liquid Haskell and FStar are other examples of things that either use refinement or dependent types to verify properties of programs. And of course, with CPS verification, we have things such as hybrid automata, and these are pretty well known as a way to express and prove properties on CPS. But the issue here is that hybrid automata tend to be very abstract, and they don't really produce executable code. So they're more of like these non-deterministic models that don't produce executable code unless you do some sort of translation step. And even if your translation is proven safe, that just adds more to your trusted code base. So as you can see here, MARVeLus, it draws upon lots of concepts in other works, but most importantly, we take all these related works and aspects of them, we combine them together into a single tool that allows the user to go from specification to implementation in a single language. So just to summarize here, robots and other CPS require formal verification to have high degrees of reliability. We can provide that by combining synchronous programming and refinement types to allow push-button verification and giving the user a definite, decidable answer to their verification problem. Finally, we do this by enhancing synchronous programming with refinement types. And we also extend the execution here to run on actual hardware, and we've demonstrated before that theory actually does work in practice. And so here's just the robot again. So of course, here's the state of the project as it is now. We go from specification to verification, and we compile things and execute. But we have identified some areas for future work. So first of all, in specification, we do want to include. Oh, okay, sorry. So we'll speed through this. So we basically want to have full LTL specifications here. So we only cover box now, but we do want to have other types of LTL formula. But we might have some issues with decidability by doing so. We also want to leverage the full expressivity of Zulus because it is a hybrid automata language. So it would be nice to verify hybrid systems. We also have tools like MARVeLus or CompCert that allow for verified production of executable machine code. So it would be nice to have a verified compiler in our pipeline here. And then finally, we would like to have some runtime monitoring at some point in our execution flow so that we can enforce these assumptions we make during verification. So yeah, here's the project as it is. Thank you for your time. And I guess if we have some time, we'll take some questions.
Okay, thank you, Patty. Time for one question.
Thanks for the talk. It's very cool. But I have a question that it looks like the type is applied to a language looks like OCaml. But to me, synchronous programming involves lots of tracking of the signal status and maybe preemptions as well, but I don't see those aspects.
Right, yeah, that's an excellent question. So the question was, we've covered all the specifications and things that look like OCaml, but maybe a language like Lisp, you might have, for example, more properties such as either causality or initialization, or like maybe compatible clocks, right? So for now, we assume that these have already been checked because we're building on top of an already fully implemented synchronous programming language. So a language like Zulus already has these checks for example, that you don't randomly access previous values in your stream, or you don't have any like circular dependencies in your state vectors. So these things are already kind of checked in the background, and we assume that they are like statically verified before they get to our verification step here. Yeah, excellent question.
Okay, so level 10. Thanks very much. Again.